Okay, I want to briefly review the material that will be on the next exam. Um, we first covered Chapter 5 on joint distributions. So prior to this, we looked at just distributions of a single random variable. So here we turned our attention to multiple random variables, initially looking at joint distributions between two random variables. And I'm just going to, in this review, talk about continuous random variables. The notation for discrete random variables is very similar. But for the joint distribution or joint PDF was actually defined as a function under an integral, and the probability that the random variables x and y lie within a particular region in the xy plane is given by the integral over that region of the PDF, so dx dy. So kind of the representation here is, if this is the x-axis, this is the y-axis, and then the PDF, fxy, is this surface lying above the xy plane. I don't know, maybe it looks something like this if you can kind of visualize, maybe a mound of sand here, above the xy plane. Take that to be our PDF. Then, of course, it's a three-dimensional surface. Then the volume above this region A, I'm showing it rectangular, but it may not be rectangular. The volume above that region is the probability that x and y lie within that particular region. Okay, and then that led to, sorry about that. That led to actually our definition of marginal Pdfs. And so these are the PDFs of x and y individually, and we can get those from the joint PDF by actually integrating the joint PDF over the other variables. So if we want the PDF of x, we integrate the joint PDF over y. Similarly, if we want the marginal PDF of y, we integrate the joint PDF over x, and then that led to this concept or definition of independence. We said that two random variables are independent if the joint PDF is the product of the marginal PDFs. Okay. Then we talked about what expected variables, what expected value meant with regards to joint PDF, and then also talked about, again, for two random variables, covariance and correlation. So the expected value of any function of the random variables x and y is the integral over all x and over all y of that function times the PDF. Actually, these should be lowercase x and y, but the joint PDF dx dy. So if we wanted just the expected value of x, we would replace this h function with just the variable x. For the expected value of y, we would replace h with just the variable y. If we wanted the expected value of the sum, we would replace h with the sum x plus y, and so on and so forth. The covariance between two random variables x and y is defined as the expected value of the random variable minus its mean, the x random variable minus its mean, times the random variable y minus its mean, mu of y. So that's mu of x, and this is mu of y. We can write this in slightly simpler form. It's equal to the expected value of xy. And again, we can compute that expected value by just plugging in the product xy here. Minus mu of x times mu of y, and these are equivalent. The correlation coefficient gives us a measure of how dependent these two random variables are, and it's really a normalized version of the covariance. We use the Greek letter rho here, and it's the covariance divided by the product of the standard deviations. And if rho is equal to 0, the two random variables are said to be uncorrelated. Okay. Then in this chapter we talked about the distribution of the sample mean, because that's very important in the subsequent chapters. And it was shown that the expected value of the sample mean is equal to the population mean. The variance of the sample mean is equal to the population variance divided by the number of observations. Again, the sample mean is 1 over n, the sum of our observations, I equal 1 to n, if we've got n observations in our data set. So it also is a random variable. It's a sum of random variables, so it would also be random with this expected value and this variance. And that's true for all underlying populations. If the population has a normal distribution, so each of our xi is normally distributed, then x is also normal. Okay. And there are only two parameters in the normal distribution, the mean and the variance, and we've got expressions for those. Again, these expressions are true in general. They're true also if the population is normal. And then I think the last thing we discussed in this chapter is the central limit theorem. Which says that if n is greater than 30, then x is approximately normal. So, and we can make that assumption that the x bar, the sample mean, is approximately normal for large data sets. So this is motivation actually to collect data with a large number of observations, because then we know the distribution of the sample mean. So I think that was it for chapter 5. Chapter 6 we went over really quickly. It was on point estimation of parameters. And we talked about two methods. One was the method of moments. And it relied on, we would set the first sample moment, which is called E of x, or the mean, sorry, the first population moment, equal to the first sample moment, which is just the sum of the xi. So this is our data. This is a theoretical value, I equal 1 to n. And the theoretical value here is going to depend on any parameters, any unknown parameters in our population. If we've got just one unknown parameter, we can solve for that unknown parameter. Again, it will appear on the left side of this equation, relate it to our data, and come up with an estimator for that unknown parameter. If there are two unknown parameters, we would just continue this. We would set the second population moment equal to the second sample moment, which is I equal 1 to n. Again, these are numbers. Once we have our observations, the right-hand sides are numbers. Now the left-hand sides will depend on both theta 1 and theta 2, but we've got two equations and two unknowns. Again, this can be extended for any number of parameters. The other method that we looked at was maximum likelihood estimation. And then there, for a single parameter, we talked about the likelihood function, L of theta. It's nothing more than the joint distribution of all of our random variables in our data. I'm going to just look at the case where there's a single unknown parameter theta. And we'll make the assumption here, typically, that these are independent. So the joint PDF is the product of the individual PDFs. And then the maximum likelihood estimate of theta is the value of theta which maximizes the likelihood function. That's a little easier, actually, instead of working with instead of trying to determine the maximum of the likelihood function, to actually work with the log likelihood function, which is the natural log of the likelihood function. Okay. And the reason for that is this natural log would turn this product into a sum. And we want to maximize this. Theta hat is the value that maximizes the log likelihood ratio, or the likelihood ratio. Again, it's a little easier to find the maximum of the log likelihood ratio that involves the sum, because we take the derivative, set that equal to 0, solve for theta. That value of theta then is our maximum likelihood estimate. Okay. Then we covered a chapter on statistical intervals. I think I gave you a handout that you'll probably want to use on the exam. We looked at a couple of different cases. First looked at a confidence interval for mu, and then looked at several subcases there. The first one we looked at is we assume the population has a normal distribution, and then that we know the population standard deviation. Again, this is kind of an unrealistic case, but it was a simple one to look at, least initially. The confidence interval here is given by the sample mean plus or minus the z alpha over 2 critical value times our known standard deviation divided by the square root of the number of observations. The other formula that was in this section is we turned this around a little bit and said, well, what if we want a particular confidence interval width? How many observations do we need to get that width, get that level of confidence? And that's given by this formula, 2 times z alpha over 2 times the known standard deviation divided by the desired width squared. Then we made the problem a little more realistic, first by considering the large sample case, and here we took as a rule of thumb the number of observations is greater than 40, and then the confidence interval here is x bar plus or minus z alpha over 2, and now we just substitute in the sample standard deviation for sigma in the previous one, and otherwise the formula is the same. And then we looked at the normal population. The normal population, again, it's a very special case because then we can exactly, there's no rule of thumb necessary, but it did require us that to talk about a new distribution, the t distribution, and the confidence interval is now given by x bar plus or minus t alpha over 2 and minus 1. So this t distribution depends on 2 parameters, not only alpha or alpha 2, but also n minus 1, which we call the degrees of freedom, times s over the square root of n. So again, the formula is similar except a different critical value. We also looked at prediction intervals and tolerance intervals for this case, for the normal population. Those formulas are given on in page 290 and page 291 in that section. And then we also looked at the confidence interval for proportion, P. And those formulas are a little bit messy, so I'm not going to repeat them here, but they're on page 280 of your textbook. And then finally, we looked at, in this chapter, a confidence interval for the variance or the standard deviation. The confidence interval would just be, for the standard deviation, would just be the square root of the confidence interval values for the variance. We only considered the one case here, the normal population. I think these formulas are on page 285 of the text. This did lead us to a new distribution, the chi-squared distribution. The confidence interval here is n-1 times the sample variance divided by chi-squared alpha over 2 n-1 for the lower bound, and then the upper bound is n-1 s squared over chi-squared 1 minus alpha over 2 n-1. Okay. And chapter 8 then was on hypothesis testing. This is the material we covered just before spring break, and first we looked at tests about the mean. Again, we considered 3 separate cases. The normal population with known population standard deviation. This is on, these formulas are on page 311. The formulas here, I think, give the rejection criteria. Again, this depends on the Z alpha critical values. And then we also looked at the large sample case. Same formulas, page 311, except now you use S, the sample standard deviation, in place of sigma. And then we also looked at the normal population case with unknown sigma. These formulas on page 317. This required the use of the T critical values. Okay, and we also looked then for hypothesis test about population proportion. I'm not going to repeat those formulas here. Page 324. And then the last thing we talked about is actually doing decisions based on p-values instead of using alpha and alpha critical values. For the p-values, there were 2 cases. There were cases based where we did a z-test, so large sample or normal population with known sigma. The p-value in this case is we calculate our sample statistic. This phi function is the CDF of the normal standard random variable. Then we calculate the p-value according to one of these formulas. It's 1 minus phi of z for what's called an upper tail test. And it's just phi of z if we're doing a lower tail test. So these different tails correspond to different types of rejection regions, or I'm sorry, alternate hypothesis. And then 1 minus phi of the absolute value of z if we're doing a 2-tailed test. 2-tailed test. Okay. And then the rule here based on p-values is we reject H0 if p is less than or equal to alpha. So previously we rejected H0 depended on the form of the test. but we compared our statistic to a critical value. If we compute p-values, we compare p directly to alpha to make our decision on whether rejecting H0 or not. I am not going to actually test you on Chapter 12, the last lecture we did that was on the linear regression. Just give you a little bit of a break since we're switching to, because that was the first lecture that I did online. I thought I'd give you a little bit of a break on the exam in terms of the material you need to study. There's certainly still a lot of material here that I've covered since the last exam. Okay.